Okay, so this is Solutions Lesson 3. Short lesson tonight. We're going to talk about like dissolves like, why certain things will dissolve in certain solvents but not others. And we're going to take a look at Table F, our solubility guidelines. So let's get started. The first thing that we're going to talk about is why something dissolves in something and maybe not in something else. So this is called nature of the solute and solvent. And we're actually going to look at an animation before we get started. So in this example, NaCl salt is added to water. Water acts as the solvent, which means that certain molecules can dissolve in it. When that happens, you can see that the negative sides of the water attract the positive Na, where the hydrogens attract the Cl minus, and dissolving takes place. As the water molecules surround each ion, a hydration shell is formed around them. This prevents the Na plus and Cl ions from forming ionic bonds again, and the salt has dissolved. So, what that showed us, I'm going to put it over here, we had NaCl, which we know is ionic, and we had water, which we know is polar. So the saying, like dissolves like, means polar will dissolve polar, and polar will also dissolve ionic. So if I take a polar solute and I put it in a nonpolar solvent, you can see that they are not alike, so it would be insoluble. It would not dissolve. If I take something that's polar and I put it in something else that's polar, so let's say I have ethanol, C2H5OH. It has this polar end. I can put ethanol in water and it will dissolve. So I have polar in polar, which is soluble. Now, as you know, I just had something ionic and I put it in something polar. I had salt, which is the solute, and I put it in water and it's soluble. But I cannot take salt and put it in a nonpolar solvent and expect it to dissolve. So this would be insoluble. However, up here I have nonpolar and nonpolar, so like dissolves like, those will dissolve. So this would be soluble. So for example, I could take methane and I could place it in propane, which is also nonpolar, and it would be soluble. And I can't take a nonpolar and put it in a polar because those do not agree, and that would be insoluble. So let's take a moment and just look at this. When I had nonpolar and polar, it was insoluble. When I had polar and nonpolar, it was insoluble. And when I had ionic, because ionic has charges and nonpolar has no charge, no pull, it was insoluble. But nonpolar and nonpolar, they're the same, they're soluble. Polar and polar, they're the same, that's soluble. And I can also dissolve ionic in polar because ionic compounds have the charges and polar compounds have that slightly partial negative and partial positive. Okay, let's look at a
scientist from the Imagination Station, Carl Nelson, and we've got blue hands, but the rest of us, we're all the right color.
with your hands now. Well, you're definitely going to need your safety glasses for this one as well.
Oh boy.
I thought we'd talk about plastics today.
Okay.
Okay, and in particular, polystyrene or styrofoam.
Gotcha.
So, Tony, if you could just uncork this bottle of liquid and very carefully pour the liquid into that top coffee cup.
When you say carefully, I know this is not just water.
Right, just go ahead and pour it in. Just
Okay.
get it in there. We'll start off with
I hear
this.
a little bubbling crude there. Hey, whoa,
Okay,
hey. Oh, my. Oh, it eats right through it.
It's right through it. So the whole thing just
What
starts
was in that beaker?
What was in there was acetone.
Ah.
Okay, it's an organic solvent. And what happens is, since the styrofoam is polystyrene that's been whipped with lots of air, the acetone will actually break apart the bonds of the polymer, and you can actually release all that air that was trapped inside. Okay?
That's cool.
So coffee cups, because they have that air whipped inside there, they're great insulators.
Sure.
You put the hot liquid inside, your hand doesn't get burned because they can be up to 98% air.
Oh, wow.
Which is, it's kind of hard to wrap your head around maybe what is 90% air, 98% air. So here's some styrofoam. Let's go ahead and just drop that right down into that
Slowly,
beaker.
we're going to watch the styrofoam get devoured,
Right.
is what you're saying.
Now, that's part of the problem with styrofoam. Yeah, just keep pushing it right down in there. That's part of the problem with styrofoam in terms of recycling, in that it has so much air whipped into it, and you can see as you're pushing that down in there, you just get like a little bit of what turns out to be a styrene polymer, polystyrene residue on the top.
It gives off a funky odor, too.
It does. You're releasing the air that's trapped inside those little bubbles inside the styrofoam. But what's amazing is you can just keep pushing more and more and more of this into there, all because it's whipped up so much. And of course, that's a problem with recycling, I was saying, is because most curbside recyclers don't want to pick up styrofoam, even though it is recyclable.
Sure.
There is a place locally, if you check out the Lucas County website, you can find out where to take your styrofoam that you get in all your packaging and whatnot. So you can recycle it, but just not on the curbside stuff.
I just can't believe it. It's like a magic trick.
It just keeps going and going and going.
There's no hole underneath the table, folks.
There's nothing there. And all you're doing is you're just breaking apart the bonds of the polymer so that it releases the air that's whipped inside. Now, polystyrene can be used for other stuff. Disposable razors, CD cases, these plastic glasses. It's all the same stuff. But styrofoam has been whipped with air. So as I was playing with this, I thought, this might provide an opportunity for a really cool chemistry demonstration. I'm thinking kids going back to school. Right? Thinking about safety. And we're being safe, right? We've got our safety glasses on.
Don't try this at home.
Don't try this at home. But we have a little... This is Carol, for lack of a better name.
Oh,
here.
Carol. You're about to get hosed.
Carol. Science teachers always have a hard time with students. They want to wear their safety goggles as a fashion statement on the top of their head. They don't want to wear them. I thought this would be really cool as a memorable moment in your chemistry class as to why you should wear protection. So we're just going to gently sprinkle Carol with a little acetone.
Sprinkle? Should I hit the face here?
Just go ahead and hit the top of the head.
Oh, I got her eye. Sorry about that.
That's okay. So again, all we're doing, it's kind of goofy, it's kind of fun.
But it's like Reanimator.
It is.
Man.
But imagine, now you got a classroom of kids, and you're talking about safety and why it's important to wear your safety gear. This is going to leave a memory. It's just kind of cool as well, right? I mean,
friends, don't let your friends melt your face. All right.
That's right.
Carl
Fun
Nelson,
with styrofoam.
always excellent to have your imagination with us here. Here are the hours for the Imagination Station.
Okay, so a little demonstration on acetone and styrofoam. So, as you can see, acetone and styrofoam equaled the styrofoam dissolving. And I think that you know that water does not dissolve styrofoam because you can take styrofoam and put it in a cup, and you can take water and put it in a cup and it won't dissolve. So the styrofoam stays intact. And that goes back to the type of bonds that are present in the molecules. Okay. Factor 2, temperature. For solids, we learned that as temperature increases, solubility increases. And we can see that in Table G. Gases, however, have a negative slope. So for most gases, as temperature increases, the solubility decreases. In an example, we can take soda and heat it, and we lose the carbonation because the molecules are moving faster, they collide more, and they come out of solution. And the third factor is going to be pressure. For solid or liquid solutes, this will have little to no effect. Little or no effect. Pressure really only affects gases. For gases dissolved in liquid, as the pressure increases, volume decreases and solubility increases. And that's how they get carbon dioxide in soda. Gas is forced into the less space per liquid. There it is, so it dissolves more. When packaged, soda is pressurized, so the CO2 dissolves in the liquid. When you open the can, you hear that which lets out the pressure. So the gas particles are released and you get carbonation. The last thing that we're going to discuss tonight is solubility, Table F. It tells you what substances are soluble or insoluble. It's used to predict whether or not a precipitate will form when two ionic solutions are mixed and undergo a double replacement reaction. And I think we looked at this a little bit in the fall, if I'm not mistaken. So a precipitate, remember, equals an insoluble product that falls to the bottom of a mixture solution following a double replacement reaction. Double replacement, two compounds switch partners. A precipitate will form, or a visible reaction will occur, if one or both of the products listed is insoluble. This is a precipitate. So let's take a look at the table. This is Table F. You have 4 columns. On the left, you have ions that form soluble compounds. So all of these ions will form a soluble compound with anything that they're mixed with, except if it meets these exceptions. And on the right side of the table, we have ions that form insoluble compounds, meaning carbonates, chromates, phosphates, sulfides, hydroxides are always going to form insoluble compounds unless we meet the exception, and then it would become soluble. So how do we use the table? Find one of the ions in your formula in either column 1, this one right here, or column 3. There are only 2 positive ions listed in Table F, so it is more likely that you will find the ion in the back of your formula. So it is more likely that you will find the ion in the back of your formula before the ion in the front. Check if there are any exceptions. That's going to be in column 2 or 4. And that will help you determine whether your compound is going to be soluble or insoluble. If there is an exception, this is important, that ion listed in column 2 or 4 as an exception will be what your ion is bonded to, then your answer is what's up here. Okay, now this, the insoluble and the soluble, is not on your reference table. You have to remember this side is soluble. If you meet the exception, the opposite happens, it becomes insoluble. Column 3 is insoluble. If you meet the exception, then it becomes soluble. Let's take a look. So I have KNO3. So this is made up of K plus and NO3 minus. I don't have any K's in my groups here, but I do have NO3 right here. NO3 is soluble, no exceptions, so that means that this is soluble. Number 2, CaCO3. Ca is plus 2, CO3 is minus 2. So I'm going to be looking for my carbonates. It's on the insoluble side unless it's combined with group 1. Well, we can see by the oxidation state that this is a group 2 element, or ammonia. So I don't meet the exception. That means my compound is going to be insoluble. Number 3, MgSO4. Mg is plus 2, SO4 is minus 2. I find my sulfates. Here they are right here. They're always soluble unless combined with Ag, calcium, strontium, barium, and lead. Well, Mg doesn't meet that exception, so it means it's going to be soluble. And the last one, my NH4 is plus and my OH is minus. I don't see NH4 listed anywhere, but I do see OH listed. OHs are insoluble unless combined with group 1, calcium, barium, strontium, or ammonium. Oh, there's my exception, my ammonium. So this is not going to remain insoluble, but it is going to be soluble because I met the exception. And that's it for tonight. Have a good night.